Okay, welcome back. So do you still hear me, please? Okay, so what we said before the break was that if you look at the fine-grained synchronization algorithm, you see that the idea is that to assign the threads different areas in the list in which they can operate peacefully, perform their operations without interference from the other threads. And this will be captured by the linearization policy, and which also implies that the safety property of linearizability with respect to the abstract data type set is observed. So first, let's go back to lock coupling, which means that you take two locks at a time and in such a way create these areas that are shifting from the left to the right. And suppose that we don't do lock coupling. So don't do this. Instead, we lock only one cell. Say in this case, only the C cell, which is the current cell. Now, as an exercise in the assignment, I will ask you to see what happens if you only lock the P cell. So suppose that we lock only one cell. So let's see what happens. So now we have the red thread here trying to remove 4. It creates its 2 pointers as usual, but now it locks only one of the cells, so the C cell. And it will do that all the time. Again, it will do the search through the list until it finds the position, the correct position, the node whose key is not strictly smaller than your key, which is the 4 here. So now, at this point of time, maybe a second thread, the blue thread, will become active and tries to remove 3. And it will repeat the operation. So it will start from the left, and it only locks the C cell, and then it starts searching until it finds the position where to remove the 3, which is this position here. And now this red thread is trying to remove a 4 by redirecting this pointer to 5, and this thread is trying to remove the 3 by redirecting this pointer to 4. So suppose that the blue one succeeds first, so now it redirects the pointer to the 4, after which the red thread performs its operation and it redirects its pointer to the next cell, which is this cell here. So now let's see what happens. Now, if you look at this list, you see that, yes, the 3 has been removed, but the 4 has not been removed. It's still inside the list. So this means that in some sense, you are not correct, because maybe some thread now will come after these 2 threads and search for 4. And it, in fact, in such a case, it does find 4 is still inside the list. So this means that the key 4 has not been deleted from the list. So you have to be careful when you define your algorithms in order not to violate linearizability. So in this case, by doing this local operation area thing, we have to be careful. And one necessary condition is that we do lock coupling. That's coupling or locking 2 cells at a time, because one cell is obviously not enough, at least not only locking the C cell. So as I told you for the assignment, I will ask you about locking only the P cell and see what happens in that case. Okay, so now the linearization policy. So it's not easy, in fact. You see that in the case of coarse-grained synchronization, it was quite straightforward to define the linearization points, because you say that at any point, in fact, between acquiring and releasing the lock, I could define that point to be my linearization point. This does not hold anymore. First of all, let's remark that for each method call, the linearization point is one and only one point. So this means that where you are executing the call, you cannot define several linearization points. And in particular, this means that when I'm doing an add here, I cannot define my linearization point whenever I do a lock or an unlock. Remember that here we don't have a global lock. So when I'm doing my searching to add the new node, I will encounter several locks, namely the locks of all the cells that I am searching in order to find the right key. So what we do is that we define the linearization point to be the time point at which I find a key which is larger than or equal to the input key, which is not strictly smaller than the input key. So this will be a linearization policy which happens to be correct in this case. So this means that in principle, what you are doing is that you are telling that your method will take effect at the point where you find the right place in which to insert the key. And the intuition is that you have found the right position, so you are in a position to tell whether you will be successful or not, depending on the key already being in the list or not. This is one thing, one aspect which is important. The second aspect which is important is that you are protected from other threats. So whenever you do your operation after that point, and before you release the locks, then you are safe. So this is somehow a refinement of this thing which we say that for coarse-grained synchronization, we can define the linearization point of a call at any point between the acquire and release of the lock. So here we say that once I have found the right locks, once I have found the key, which is not strictly smaller than my key, then this is the point to linearize, because I will report the correct result through the return, one of these two returns, because I know which key I am, I have, whether I have the key or not. And by these two if statements, I will return the correct result. But also during that time, nobody will be able to come and interfere with me. I will have concurrent calls, overlapping calls, touching other parts of the list, but not the one that I am working on myself. And equivalently, you can say that this is the time point at which I lock the cell with key larger than or equal to my input key. So this is where you define it here or exactly after this in the while loop, when you go back to check the condition of the while loop and you are about to exit. So let's see what happens if we apply this linearization policy. Let's look at some scenarios which arise when I define my linearization point like this. So again, to remind you, when you define the implementation of a concurrent data structure, as we are doing here, it's not enough that you have the code, but also you have to give me the linearization policy. The linearization policy by itself is not part of the code, but it's a guarantee that you give to the user of your code. So let's make this more clear. Let's see what happens if you have one thread only, as usual, which is active, and then we try to run several threads, 2 threads, and then several threads at the same time. So suppose that I have the red thread, which is trying to add a 4. Now, what happens is that, as usual, the thread will come and lock, as we say, the first. So the thread has become active. This is the time point at which the thread became active. So the first thing it does is that it locks the head of the list as usual. And then it creates its 2 pointers and let them point to the first 2 cells and then locks the next cell. So now I have my 2 locked cells, but I still have not found the key in which, or the position in which I need to insert my key, or which I need to check whether to insert the key or not, because I'm still here. So this means that I have to run the while loop one more time. And that's interesting because you see here, the linearization point is not exactly one line of code. It's a particular execution of a statement inside the code. So when I run this while loop now here, I will not encounter the position at which to insert my key. So this means that while I'm here, I cannot define my linearization point to be this one. While in the case of coarse-grained synchronization, in fact, there was a particular point which you could point to and say, this is whenever I execute this line, for instance, the lock, the acquiring of the lock, then this is my point of synchronization. Here you say that it is this line, but this line will be executed several times. And it's only one particular execution of this statement, the lock here, which corresponds to the linearization point. And this is exactly the point at which I have found the key to compare with my key, the first key, which is not smaller than my key, which in this case is the 5-year. So this is my linearization point now. I have run the while loop one more time, and now I have reached here where I can linearize. So this is the linearization point here. So now I have found the key, but remember or see that I have indeed not inserted the key itself inside the list. But nevertheless, I say at this point, it takes effect. So it is fine to tell the other threads that I have already inserted the key, because I am going to insert the key anyway, and nobody anyway will be able to look at it before I have released the locks. And I will not release the locks before I have inserted the new key here. So you see that this notion of linearization is abstract. It's already getting non-trivial. You see some of its properties here. So just it's a logical time point at which you tell the other threads that my operation has been successful or not successful, and it has changed or not changed the state of the data structure. So everything will be more refined now. So already here, it's not easy to reason about the correctness of such an algorithm. And things will be even more complicated later. In fact, there are algorithms where the linearization point of one thread will be given by the execution of another thread, which is quite interesting. I think I will make this one problem in the last assignment just to see. It will be quite complicated. Yeah, so let's go back to this example here. So here I found the position inside the list in which I insert my key 4, but I linearize before physically inserting the key in the appropriate position. So here now I can go ahead with this. I have the if statement that says that indeed the key is not, the key of the cell that you have found is not equal to your key. It's 5, not equal to 4. So you can go ahead and insert the new cell there. And then now I unlock, and now these cells can be accessed by the other threads, and there my call will terminate. So I initiated the call, I linearized when and only when I found the right position to check, and then I returned when I finished the call. So the call by itself overlaps these time points, but the linearization point was one particular instant in which I found exactly the position where to put my so good. So any questions up to now, please write in the chat. So now let's look at several threads executing concurrently, and whether it's add or remove, the linearization point is exactly the same as the point at which you find a key which is not smaller than your key. So suppose that we have 3 threads, I think, like this. They are trying to perform different operations concurrently. The green one is trying to add a 2, the red one is trying to add a 7, and the yellow one is trying to add to remove a 7. So now all of them are active, and then one of them will get access to the first cell, which is pointed to by edge, the sentinel node, the leftmost sentinel node. And suppose that is the red. So now what it will do, as usual, it locks the cell here, and it locks the next cell. I will not show the pointers in this example because the pointers are always pointing to the two locks that are taken by the thread. So I think this should be easy, just to make the picture a bit easier to follow. So now the red thread looks for the position in order to find the cell. So it will start traversing the list. Observe that it's still not there. So it has come to this position, at which point the yellow thread will become active. And the yellow thread is trying to remove a 7. So you see that there is a clash between the add 7 and remove 7. And as you'll see later, the order of the linearization points and the results reported by these two threads will depend on the order in which they entered the list. So in this case, the red entered first, and now it has reached to this point. The blue will become active, and it will try traversing the list. There is nothing preventing it from starting the traversal because the first cell is not taken. So it will start its traversal, and then it starts searching the list until it comes to this position where it has locked these two cells, but it cannot proceed from here on because now you see the barrier to the red area. So now this is what we say, the yellow has come this far, but it cannot overtake this thread, although its relevant position is also here. The one which entered first has priority, if you wish, in this algorithm. So it's the red one who will be able to add before the yellow one will succeed. So now the red one becomes active again, and it will reach the position where it can now check whether it needs to add the cell or not, or the key or not. And in this case, it checks, as we know now, by now, that the 7 is there or not. It's not there, so it will be successful. And this is the linearization point. You see that this is the linearization point for the red because it has indeed reached the position in which it can insert the cell. And it knows it will eventually do that because on the one hand, it has all the information it needs. It has found the key, the first key, which is not smaller than its key, and nobody will interfere here. So it will already here, it can tell the other threads, fine, I have found my linearization points, and this is the point of time I declare that my operation took effect, although in reality it's not, because it will insert the cell later. Okay, so now encouraged by the fact that this area has become free, the yellow one tries its luck and it continues its traversal, but then it will be stopped there because it cannot continue beyond that position. So now the green one will become active, and it's trying to add a 2. And indeed, this part of the list is free, so it can enter the green one. It locks the relevant cells here. It has already found its position here. This is the linearization point, time point at which I find the keys larger than or equal to the input key. The 3 is larger than the 2, which it is trying to add. So it will linearize here. So observe that the green linearized after the red, although the red started after the green. So now the blue thread will become active, and it will try to remove a 2. But the green one will become active again, and it will indeed add its 2 here, and it makes these nodes free, and now it has terminated. So the green one has done its job. It has inserted the 2 inside the set, and it has freed the cells. So now the blue one becomes active again, and it will try again to remove the 2. So now it can enter, find its position here, and this is its linearization point because it has found the first key, which is not strictly larger than its key, which is 2 here. And this will be its linearization point, and it will obviously succeed. So this is the linearization point. And now, sorry. So let me go back. So the 2 has succeeded in finding the position. the correct position, and therefore it has linearized also. But now, before it succeeds in removing the 2, the red will become active again. And what it does is that it will indeed add the node with key 7 inside the set and terminate. So this is what it has done, and it has terminated. So let's see who will become active next. In fact, I don't remember myself. It seems to be the blue one here. So logically, I think it's reasonable that it completes its operation by removing the 2 from the set. And this is what it does, and it terminates. And the only one which remains is the yellow. And now the yellow can proceed, in fact, and find the key in which its operation area, which is exactly the 7 here, which is not smaller than its key here. So it will be its linearization point like this, and then it does delete the 7 and it terminates. So you see that this is a concurrent history that we generated by running the program. Not only that, on the fly, we generated also the linearization points. So now what we have is this concurrent history here with the associated linearization points, which means that you can view it as a sequential history, which is very nice. So you see this algorithm, which is not trivial, although it looks very simple, but this can be deceptive, in fact. So in fact, already here, there are thousands and thousands of different scenarios in which different threads can interact, and doing formal verification for such a program is not trivial. But anyway, the methodology is clear. What it does is that gives you a concurrent history, at the same time gives you the linearization point. So now what you have is that you have a sequential history, because you have the first linearization point corresponding to this method call, and then you have the green one corresponding to this method call, and then you have the blue one corresponding to this method call, and then finally the fourth linearization point is this one here, which gives you this one. So now from this from the concurrent program, we got a concurrent history. From the concurrent history, we got a sequential history. And from the sequential history, now we can get a trace. So this completes the picture in a nice manner. So this is what I said in the first or second lecture, is that although we have these concurrent programs, and it's not clear what it means in the first place, to say what a concurrent program, that a concurrent program is correct, what it means. So now we have a concise definition. So a concurrent program is linearizable with respect to an abstract data type if all its histories are linearizable with respect to that abstract data type. So this means that for each history, you should be able to give me linearization points from which I can generate a sequential history, from which I can generate a trace, which satisfies the abstract data type. Okay. So now if you go back to the previous example, and remember I told you that you had these 3 threads, and now the red entered before the yellow, which means that the yellow had no chance to overtake the red. And in fact, the same thing happens if the yellow enters the list before the red, and it tries to remove a 7, and now it goes there and linearizes because it has found the right position in which to linearize. And now the red one will become active, and it will try to redo the same procedure. It goes all the way until it's about to enter the 6, but then it has a barrier of the yellow thread because the yellow thread has taken the lock for the cell. So this means that the red has no chance to finish its operation before the yellow does. And this is what happens now. The yellow can do that. It looks at the cell and says, it's equal to, it's not there. So it's not equal to the key I'm trying to remove. So this means that I will return false. So, and I release the keys, the locks. So now the red will become active, and now it can acquire the locks for these 2 cells. And it says that, okay, the 7 is not there, so I linearize, and then I can insert my 7, and everybody is happy. So if you compare to this history that we generated with the previous one, if you project on the red and yellow threads, you see that in the previous one, the red entered the cell, the list first, followed by the yellow, and this was reflected by the linearization points, because this one will linearize before this one, which means that you get true and true, which is good, because this is a valid history. In fact, if you take this linearization point here, you see that first I'm successfully adding a 7, and then I'm successfully removing a 7, which is a valid behavior of the abstract data type set. If you look at the second history that we generated here, it was the opposite, but the program is still correct. But this is another scenario, another interleaving, another non-deterministic behavior that arises due to concurrency. The yellow one will enter first, followed by the red one, but fortunately, you see that the yellow, it came to the correct conclusion. It says that the 7 is not there, so I am saying false, but the red says that I don't have a 7 there, so I'm saying true. So here in the end, you don't have a 7 in the set. Here in the end, you will have a 7 inside the set. Okay, any questions? Okay, otherwise I will just give you a hint about optimistic synchronization, what it means. And then I will go through it in detail on, I think the next lecture is on Wednesday. So on Wednesday, I will do optimistic synchronization. Next week, that we'll have a lab. Remember, no lab on Friday. I will send this in student portal, and of course also. And then we will have a lab next week. And then the week after, I will go through lock-free algorithms, but now in the context of stacks and queues rather than sets. Anyway, so what's the idea with optimistic or synchronization? So the idea is that something that I'll come back to also in the next lecture. So while fine-grained synchronization is better in many cases than coarse-grained synchronization, it has its own disadvantages. And the disadvantages, in fact, so let me go back to these slides that I had somewhere. Many slides. It has taken a lot of time to produce these guys. Here. So you see, this illustrates the disadvantage quite nicely. Namely, you are operating in a pipeline manner. So this means that the threads that are, as we saw in the examples that we studied, the threads that are inside the list, they block subsequent threads from overtaking them. So this means that if you have a slow thread here, which is working here, and then you imagine you have a very long list, you have a slow thread here, which is working very slowly, and then you have other threads that are trying to go beyond and operate on the later parts of the list, then all of them will be blocked by the slow thread here. And it's not easy or it's not clear how to fix this. I mean, of course, you can have something here which gives priority to threads that are manipulating higher nodes with higher key values, but this is not trivial. And also maybe when the green thread, which was the slow thread, when it enters the list, it was alone. And it was only after a large number of threads arrived that can operate much more quickly than the green thread, but their problem is that they cannot go beyond the green thread, which is slow. So this means that the whole throughput of the system will come down, and the performance of the whole system will be not very good. So because you will not exploit the concurrency. And this is the main goal with concurrent, as we said in the beginning, with concurrent algorithms. Be correct, but try to exploit concurrency so that you are efficient. So we remember in the first lecture, we talked about the trade-off between efficiency and correctness. So the more efficient you try to get, the more complicated your algorithm will be and more difficult to get it correct, but the more efficient you get. So there is this trade-off. And here you see one example. So it's more efficient than coarse-grained synchronization, but on the other hand, it has its own bottlenecks. So the idea with optimistic synchronization is not to lock the cells at all in the beginning. So the idea is that don't lock the cells, but once you find the correct position in which you want to operate, once you have identified the cells in which you want to operate, then you lock it. You will not lock all the cells. I mean, you see that this algorithm, all the threads, they have to lock and unlock a large number of cells. And in fact, locking and unlocking is a costly operation. So you would like to reduce the number of locks or the lock acquirement and releases that you are performing in order to reduce the cost. So in this algorithm, regardless of whether you are going to use a cell or not, you are locking it before you go to the next one. Well, the idea of optimistic locking is that, or optimistic synchronization is that don't lock until you find the relevant cells, and it's only 2 cells that you are locking. So the number of locking operations will be much smaller. But the disadvantage is that, as we will see later, if you only lock the 2 cells that you find here, then once you are about to perform the operation, these cells may have gone. They may have been removed by other threads. So this means that in such a case, when you are about to perform the operation and when you have locked the cells, you have to check again that the cells are already there, are still there, sorry. So again, and of course this I will make much more concrete in the next lecture. In optimistic locking, what you will do is that you don't lock all your path when you are getting to the correct position. You find the position, and once you are there, it's only then you lock. The price you pay is that the cells that you have locked may have been deleted by other threads. And so you have to check that the cells are still there, and if they are not there, then you have to backtrack, you have to redo the whole operation. Now, the philosophy of this algorithm is that the probability that several threads operate on the same cell is quite small. So typically, if you have a set with thousands and thousands of elements and you have thousands of threads, then the probability that 2 threads will be operating on the same cell is quite small. So this means that even if you lock 2 cells, the probability that they disappear, so the only reason why they have disappeared is that because some other threads was operating on the same key values, and therefore it happened to remove these cells. So if this probability is small, then you don't have to do the backtracking. So the algorithm will be slow only if you are forced to do the backtracking often. In such a case, the performance will become worse and worse. So just to repeat one more time, for optimistic locking, we don't lock until we find the relevant cells. When we find the relevant cells, we check whether they are still there or not. If they are there, then fine, you just perform your operation and you are done, and you locked only 2 cells, so very efficient. If they are not there, then you pay the price. So you have to go back to the start of the list and redo the operation again. So this means that if you don't go back to the start of the list often, then you have good performance. If you are forced to backtrack and restart the operations many times, then your performance will not be good. And typically in applications, because different threads will operate on different cells, this means that the probability or the expected value of backtrackings that you have to perform is small, and therefore the operation, the algorithm is usually efficient. So this is the philosophy of this algorithm. And then we, in the next lecture, which is on Wednesday, I think, we'll try to make this more concrete. So you see that what we will be doing is that we have our while loop, so a friend from before, but there are no locks until you exit the while loop. So you find the key that you want to check, and then only after that you have found the key. So inside the loop, you don't lock anything. There are no global locks, no locks inside the loop. Only you lock only when you have exited the while loop, which means that you have performed or found the right position. And then you do this validation. This validation is what I told you. Namely, you validate that the two cells are still there. And if yes, you perform your operation. If not, then you unlock, and then you go back and redo the loop again until you succeed. And if you succeed, then you exit. So this while true corresponds to the backtracking. So you backtrack, you repeat this loop until you succeed. But if you succeed, then you exit the loop. And this is the high-level intuitive description of the philosophy of optimistic synchronization and one way to implement it. As I told you, although we do it for sets, this can be repeated for stacks and queues. And maybe I'll ask you to do that in the last lab, where we will work with stacks and queues and look at different algorithms for manipulating stacks and queues. Okay, I think this is what I had to say for today. So if you have any questions, please go ahead and ask. Otherwise, so see you next time. Thank you.